Diskusie pod lampou existujú iba vďaka vašej podpore. Ak považujete program pod lampou za zmysluplný, pomôže nám už 1 euro za diskusiu. Vopred vám veľmi ďakujeme.
We are very grateful to have you here, and in half or 3/4 of hour I want to discuss with you the recent very exciting observations, direct observations of black holes. We have seen them for the first time, we have heard them for the first time. But before that I want to ask you about the start of your career 60 years ago, and my question is this, that you were studying at Caltech, where at that time the professors were Murray Gell-Mann and Richard Feynman, and this was the absolute peak of the particle physics, the 60s and 70s. In spite of that, you choose the general relativity as your field, which at that point seems to be not very observative science, with not great chances to be observatory science in your lifetime. So it happened that in the last years, the particle physics is not that exciting as it used to be, and black holes physics, for example, and well, when you started, even the cosmic background radiation was not discovered yet. So why did you choose this path?
Because I fell in love with the idea of space being warped and time being warped. I just found this terribly fascinating, very hard to understand, and so it was intellectual curiosity. And so I was at Caltech. Yes, that was the character of Caltech. But I decided to go to Princeton because the most creative person working in relativity was John Wheeler. He was at Princeton. When I did research as an undergraduate with a truly great astrophysicist, Jesse Greenstein. And when I told Jesse that I was going to Princeton to work in general relativity, he warned me that there's no sign that relativity would be relevant to anything in the universe except the universe's expansion, and we already know about that. And nevertheless, I really wanted to understand these phenomena, so I went to Princeton.
Okay, and then you came back to California and became a full professor at the age of 30, or?
I have to think. No, I became tenured, which associate professor at the age of 29.
29.
And then a full professor, I think, about 2 or 3 years later.
Mm-hmm. And about that time, you already co-authored the gravitation Bible called Gravitation. I have it here, showing it to camera. Well, for me, it's one of the 3 best books which I ever read in
Did you read this? I didn't know anybody read the entire book.
No entire book, definitely not. Mostly only the track 1.
Yeah.
This is the book just for our
large numbers of physicists have learned from this, but they don't read the whole book. They read half of the book.
That's almost impossible. Yeah. Well, the other 2 are Jackson's Classical Electrodynamics, and I don't know if you are familiar with Ashcroft and Mermin's Solid State Physics.
Yes.
That's a wonderful book also. They are quite different, these 3 books, but this one is... so that's my second question, that from the very start of your career, you were also interested, almost devoted to teaching. Why is that? There are many scientists who are only focused on research and take lecturing as something which must be done, but they are not very fond of it.
So I enjoyed teaching. I recognize teaching as the way to inspire young people at Caltech, very talented young people, and initiate them in research so that my impact on the world of science would be far greater than I could do by myself, by creating an environment in which younger people could interact with each other, understand from me and colleagues what the most interesting problems were, and solve them more rapidly than I did. And so it was partly that, to inspire, the payoff from inspiring young people, and partly just enjoying it. Let me return to your remark about when I was a student at Caltech. Elementary particle physics was tremendously exciting, and relativity was nothing.
Absolutely.
By the time I was back at Caltech, and this is only 4 years later, that happened to be one of the periods when elementary particle physics theory had slowed almost to a stop. There would be exciting periods after that, but it happened by chance to be a period when particle theory was moving very slowly. And so I returned to Caltech, and within a year I had acquired basically the 5 best theory students at Caltech working with me.
As PhD students.
PhD students.
Mm-hmm, mm-hmm.
Because relativity was starting to take off. This was the early period of figuring out the properties and behaviors of black holes. And so I just happened to enter the field at just the right time when the transformation of theory, not observation, but the transformation of the theory was happening extremely rapidly, in large part because of John Wheeler.
Please remind me, the Kerr matrix was discovered
in
at
'63.
In '63.
While I was a student at Princeton.
It's just for people who are watching us. It's the geometry of the warped space-time around not the static black hole but the rotating one, which I would say that Einstein was. It was possible for him to reject the idea of black hole because for the Schwarzschild metric, for the static black hole, he can say that this is such a special object. It cannot be present in our universe, but with rotating holes and exhibiting the same paradoxical or very interesting. So was this discovery of the geometry of a rotating spin hole one of the triggering moments of the whole?
That was one of the triggering moments. The other triggering moment came in 2 parts. A part in 1939, the same time as Einstein was rejecting black holes. Oppenheimer and Snyder, who were at Berkeley but spent their summers at Caltech, they did a theoretical calculation of the implosion of a star which has lost all its pressure and discovered the formation of a black hole, though they didn't understand the mathematics at all well, and other people didn't either. So I spent a lot of time in Russia in later years, and when I discussed this with Yevgeny Lifshitz, one of the really great Russian physicists of this era, and so this discussion was probably in 1968. Lifshitz says, you cannot imagine how completely confused we were about this calculation of the implosion of a star to form what we now call a black hole. You simply could not understand what was going on. And so it required until about 1965 for physicists to really understand the mathematics of the formation of a black hole by implosion, even though the mathematics was done, but not properly interpreted already in 39. So 65, that's the year I completed my PhD thesis, was really the major turning point in the theory. And from that point on, the Kerr metric came in 63. The discovery of the cosmic microwave background came in 64. By 65, we were understanding this calculation of 1939 of Oppenheimer and Snyder, the implosion of a star to form a black hole. And they knew, and quasars were discovered, quasi-stellar objects, which were objects that by 65 we understood were some sort of gigantic explosion in distant galaxies. And then pulsars were discovered, which turned out to be spinning neutron stars. A complete transformation, all of these phenomena, things where general relativity was important. And so yes. I entered at just the right time, absolutely the right time. And so in some sense it was luck, but in another sense it was something that has happened through my career. I made wise choices, I think, because I could see the hints that things were going to happen if we pushed in certain directions. And I was able to contribute to making them happen. And so this field for theory began to take off at that time, and for experiment it came a little later.
Okay, one of the paradoxical features of the black holes is that mathematics, when the black hole, when we are discussing the formation of the black hole, the mathematics is very complicated. The physics of the materia which is imploding is complicated. But then it turns out that black hole itself, at least the exterior of the black hole, is well, parameterized, meaning everything is said by 3 numbers, one of which is usually 0. So basically by 2 numbers, the mass of the black hole and the amount of rotation, so to say, the spin of the black hole. How was this taken in the community when it turned out that the thing so complicated is such simple at the end?
It was an amazing discovery, and in the community it was just breathtaking to see this happen. Our understanding of this came somewhat gradually. We saw hints of it from certain calculations, stronger hints from other calculations, and then rapidly in the early 1970s, a series of proofs of rigorous mathematical theorems that led by roughly 1973, 72, 73 to a pretty firm understanding this was the case. And so we sometimes call this the uniqueness of black holes. John Wheeler called it the theorem that black holes have no hair. And that there are no other there's no other free parameters, no other things besides these 2 or 3 numbers that can affect the properties of the black holes. Let me just say that for me, getting an observational proof of that was one of the goals of creating gravitational wave astronomy, which we presumably will get to. Yeah. But I'll just point it out at this stage that the things we were studying as theorists in the early 1970s, this and other properties of black holes, became the goals to turn this into observational science, became the goals of much of the rest of my career.
If the black hole is so simple object, and if everything about the outside of the black hole is known, is given in the Schwarzschild geometry and the Kerr geometry, then the question is, what else is to be done there, which is tremendous field. But what I want to say that for the general public, black hole is something from which even the light cannot escape, so we can learn basically nothing about it just by definition. Seemingly it's so. Now, in the last 10 years, we have seen the movie Interstellar with your way of depicting the real giant, very fast spinning black hole. Then we heard via gravitational waves the merging of two black holes, and after that we have seen the black hole. So my next question is how we can see the black hole and then how we can hear it.
So if you have a black hole sitting alone in the universe, you won't see it because it's black and the universe is black. But if you have the black hole sitting here and the universe is filled with stars, then the black hole will make a shadow against the stars. The light cannot go through the black hole and come out the other side, so it'll be a black circle or some shaped object on the sky hiding the stars. But it becomes much more interesting than that because the light rays that bring us the image of a star, because the black hole has such strong gravity and because it is warping space and time, a light ray from that star can go near the black hole, go around the black hole several times, and then come to your eyes.
From different directions.
From different directions, and going around the black hole a different number of times. So you get many images of each star. And if your camera is in motion around the black hole, then that pattern of images is obviously going to change from each star. And so as a camera goes around the black hole in orbit, you see an amazing pattern of light from the stars, a changing pattern, which was first really explored in great detail with the computer program that was written for the movie Interstellar. But after we made the movie, because in Interstellar, the black hole has a disk of hot gas around it. And that disk is so bright that it hides the light from the distant stars, and so you see something else. But that example of a shadow against the distant stars just points out that you can get very rich observations.
Yes, we are speaking about this picture
that's
here.
That's the picture, that's right.
And that's something I want to spend some time on that picture with a little bit detail. So here in this picture, and I think it's the director's decision not to have the stars we were speaking about in the background. So
well, the stars could be in the background, but the hot gas that's around the black hole is so bright that it's like trying to look at the stars in daytime with a very bright sun shining.
Okay, so but this effect is not visible here.
Yes.
But another even more fascinating and dramatic effect is seen here. What we see here is the black hole and something called accretion disk around it, which is the disk of a very hot and radiating gas. And usually people would think that we see it going in this or that direction around the black hole in this plane, and there is perhaps some other disk which we see from this, which is absolutely not the case. So can you explain us how the space and time, but in this case the space is the point, is warped around the black hole, that we see only one disk which is in this plane, and this is just a optical, not illusion, because we are really seeing it. But
so in this case, the disk is in this plane.
Yes.
And so what you see there is the disk. The camera is just above the disk, and so you see the front top of the disk here. But actually, the light from the back part of the disk, so we go around this disk and get back behind.
It's behind the computer.
It's behind the computer. That the portion of the light that heads toward us gets swallowed by the black hole, so you never see it.
Which is going directly in our direction.
It would be coming directly in our direction. But the light from the back part of the disk that is going up can go up over the black hole, and it's pulled back down by the black hole's gravity and the warping of space and time. And so this is light that we see that is coming back down, but it began going up from the back of the disk over the black hole, now coming down to the camera. So the camera thinks that the back top of the disk is in that direction, but actually it's seeing it by light rays that are coming down by having traveled over the black hole.
Okay, so what we see here is the part of the disk which is actually here,
yes,
and the light is going in this direction, so when it is coming to our eyes, we seem to see it here,
yes,
and this is the same thing going downwards.
That's right. That's right.
Okay, and another thing that the first guess of not too educated audience would be that what we see, this shadow, many people have heard about horizon of the black hole, and I would bet that 99 people from 100 would think that this is the horizon of the black hole, which is not the case.
No.
So how can you explain us why the horizon is not here but at two-thirds?
It's a smaller radius. So at this place, the inner edge of of this image is a location at which light rays can go around in a circle over and over and over again. They're trapped in a circle going around the black hole. And down, anything that is emitted from the horizon will go, either it will go straight out or it will go up and back down into the horizon. It's basically, almost all the light rays are trapped if they come out from the vicinity of the horizon, unless they go directly straight out.
So the common knowledge about black holes that nothing can go through the horizon from inside to outside is right, but the black space is larger than this.
Larger than this.
1.5.
Yeah. If the black hole is not spinning.
If it is not spinning, in Schwarzschild metric, yes. And okay, and this bright circle inside it is this shell of fire.
Yes.
This photons spinning there. But not forever, because sometimes they collide with something, or because of electromagnetic interactions.
But also
they are
because
able.
If they're just a little bit outside that location, they spiral out.
Yes.
If they're just a little bit inside, they spiral into the black hole.
Yeah.
So you have to be at precisely that location to go around and around.
And if the photon is somehow deviated, then some of them can approach the camera. We are not speaking about the observations from the Earth. This is the picture seen by the camera, which is close to the black hole.
Yes.
Now, what happened recently is that we have, maybe I have it here. Yes.
Yes.
This is the real picture of the black hole, taken from the pretty large camera.
A camera basically the size of the Earth.
yes, exactly. Because of telescopes taking the picture from different places on the Earth within the Earth rotation. And this is the real picture of something around the black hole. in M87 galaxy, in the core of the galaxy. Now, can you explain what we see here and how does it, which part of this, if any, corresponds to your Gargantua picture?
So if this black hole had a disk that is thin, then the disk is in that plane, and you're looking down on it, and so you just see a circle. Okay.
Yes.
Let me comment a little bit further. Well, no, let me back up. And so that explains why there's no crossbar, because the disk is in that plane. In reality, we know from some details of this that the gas is actually in sort of a thick disk, and it's swirling all around basically in this direction. So there's a complicated gas flow. But when you look through this part of the gas, you see lots of photons emitted because you're looking through a deeper amount of gas than if you're looking toward the center.
We're speaking about the bright side.
No, anywhere here.
Okay, cool.
So the amount of gas, the gas. Think of the gas as being like a moderately thin sheet. If you're looking at it from this direction, say that thick a sheet, if you're looking at it from this direction, you're looking through the sheet, and there's lots of gas in there. If you're looking down on it, and the gas is going in front of the black hole, you're not going through that much gas because you're going through the thin sheet. And so there is some light shining from in here, but it's far less than out here, because out here you're looking parallel to the sheet, and in here you're looking through the sheet. And so that's probably what's really happening. Now, you ask, why is this bright on one side and not on the other?
And bright spots, yes.
Yeah. And the issue is that the gas is moving toward us on this side, and so it is brighter due to Doppler shift than on that side. It's brighter and it's less red than on that side. Now let's go back to interstellar. Okay, can we go back to the interstellar
of course.
black hole? Because this is very interesting.
Let me see. Okay, here it is.
Okay. Now, and so I had this conversation with Christopher Nolan, the director, and I said, look, this disk is going around like that. This side where it's moving toward us, it should be brighter and less red, and that side where it's going away from us should be dimmer.
Exactly, because what we were speaking about.
Yes, that's right. And Christopher Nolan said to me, yes, but you did not take into account of the property of the human eye. When you have something very bright, the human eye cannot distinguish colors very well, and it cannot distinguish the difference between a factor of 2 or 3 in brightness. It just can't. And I want a movie that characterizes things the way the human eye would see them. And so we're missing something that really is there. It really is less red on this side, and really is brighter, but the human eye can't see it because it's so very bright.
Okay, so director Chris Nolan refused the more realistic picture of the black hole?
No. He said, when you take account of the fact that it is a movie audience looking at this, and this is supposed to be the way an audience would see it if they were there, the realistic picture is, because of the limits of the human eye, it will look like this.
Okay.
So if we had a very good camera with a very good film or pixels, we would see this effect. But if you're just looking at it with a human eye, you won't see this. So this is a little complicated. The other thing is that there's a bright glow here, where that should be a black shadow. There's a bright glow. Why? That's due to scattering of light in the lenses of the camera. And so in making the movie,
Okay.
And it is true, when we did the computation, ignoring the properties of the human eye, ignoring the properties of the camera.
The picture was different.
It was different. This was completely black in here,
Yes.
completely black. But the simulation, which was done by, the details were worked by Oliver James, who was chief scientist at Double Negative, or DNEG, company that did the visual effects, and they're superb. They got the Academy Award for the visual effects. He propagated the light from the black hole, from around the black hole to the camera through an IMAX camera, including the details of the lenses in the IMAX camera, the details of scattering of light in the IMAX camera, which causes this glow to the human eye, and through the human eye, which cannot distinguish.
So I'm learning something here. I got it wrong. I thought that the image of the black hole in the Interstellar was less realistic than the realistic one, but it is the other way around.
Well, the realistic one is the one that a scientist is interested in. The scientist always wants to remove the influence of the instruments that are used to make the measurements, and determine what would be the answer if you were looking directly at the light with a perfect eye, and so that's what the scientists produce, and that's what the actual photographs look like, but the goal is different in a movie.
Yes,
and there you include the effects of the imperfect behavior of the instrument, the telescope, and the imperfect behavior of the human eye.
Okay, let's now proceed from how we see how we would see the black hole when being in the vicinity of it, and how we have seen it from the Earth using the camera of the size of the Earth, to how we heard the merge of two black holes and many other things. That's for what you got the Nobel Prize.
Well, I and colleagues, yes.
Yes.
I shared the Nobel Prize.
You shared the Nobel Prize. In fact, it was a collaboration of about 1,000 people.
1,000 people, that's right, yeah.
So I want if you can explain us how we can hear it, and why the calculations of the sound were much more complicated and involved than the calculations of the light coming from the black hole.
Yeah. So let me begin by some fundamental physics. Okay. When we look at the laws of physics, or some would call them laws of nature, that control the universe, that enable us to predict what happens in the universe, or explain what's going on. These laws of physics tell us that there are only two kinds of waves that can begin at some object very far away and travel across the universe to Earth, bringing us information about their source very far away. Electromagnetic waves, and this includes light, X-rays, radio waves. These are all oscillations of electric forces and magnetic forces. So that's one kind. And the other is what we call gravitational waves. And these gravitational waves are really, we can talk about it in a moment, really ripples in the shape of space that travel from far away to Earth, bringing information. Galileo was the first person to build an electromagnetic telescope. It was a little optical telescope pointed to the sky. He pointed at the moon, at Jupiter, discovered Jupiter's 4 moons, and saw that just as he believed the planets went around the sun in orbit, rather than the Earth being at the center of the solar system, just as the planets go around the sun in the orbit, these moons go around Jupiter in orbit. That was a great discovery. but it was the beginning of electromagnetic astronomy. And this electromagnetic astronomy has completely changed what we know about the universe over a period of 400 years. And so our goal in the project, the LIGO project that I worked on with 1,000 people, was to do for gravitational waves what Galileo did for electromagnetic waves. For the first time, to be able to do gravitational astronomy, looking at distant objects with this other kind of wave. And so this was our dream when we set out to work on this, Ray Weiss and I, both of them about 50 years ago, and it took close to 50 years to realize it. And so these waves, and this is the other thing I wanted to say, and then I'll turn it back over to you. What these waves do is they stretch and squeeze space. So if these waves are coming from you to the camera, well, to that camera. I understand there are several cameras here. Anyway, if they're coming away from you, they stretch space in this direction and they squeeze in that direction. And then they stretch in this direction and squeeze in that direction. And this oscillation of stretching and squeezing is the physical nature of the wave. But the phrase stretch and squeeze space is not as precise as what I would like to do for you and this audience.
Okay.
So what does that mean? So we as physicists, we talk about inertial frames, and by this we just mean in some little region of space, we can put a bunch of particles in there and make them be basically at rest,
Yes.
in some sense.
Yes.
And then we just leave them alone. And they will remain at rest in what we call an inertial frame. But just a bunch of particles over here at rest with respect to each other, and let's say at rest with respect to you and me. And we do the same thing with a bunch of particles over here. And the strange thing that happens is when a gravitational wave comes by, those particles move back and forth, respect each other. But there's no forces between them making them move back and forth.
It's just the geometry.
It's just geometry of space and time. It's the stretching and squeezing of space. We think of them as riding on the space that stretches and squeezes. That doesn't mean that I'm being stretched and squeezed. I have very strong electrical forces inside my body that resist the stretching and squeezing, so I don't get stretched and squeezed. So it's just
this lattice of the point of particles.
Yeah.
These are particles which do not feel any force from the other particles and from whatsoever in the universe. So what they feel, the only thing is really the geometry of the space-time, and they are moving in this direction and stretching here, and so the stretching and squeezing is the movement of these particles.
Yes,
okay,
exactly.
understood?
Yeah.
And now, the second part of the question was, why the calculation of how the gravitational waves, they behave like this far away from the source of the gravitational wave. Why the calculation of how they were originated is so complicated that it took almost longer time than to prepare the experiment, which took decades.
So the strongest source of gravitational waves that we have in the universe today is collision of black holes. And I already knew with high confidence, not complete confidence, but pretty high confidence in 1980, that would be the first thing we would see. From some arguments, I won't go into the details, but so that was, 35 years before we saw the waves. That I was already pretty sure that was the case. And so then the challenge was, in order to understand what we're seeing, we need to know what is the nature of the waves produced when black holes collide. But the collision of black holes is a very complicated process because the black holes are not made from matter like you and I. They are made from warped space and warped time. The warped time is that time slows down near the surface of the black hole. Time slows to a halt at the horizon. That space, the diameter of a black hole is very much larger than the circumference, which doesn't happen under normal circumstances. And that the spin of the black hole forces space to whirl around the black hole like the air in a tornado. The spin, that whirling motion, just like in a tornado, near the black hole is fast, farther away it's more slow. That means that that somebody sitting here looking at, let's say, a gyroscope, which behaves, we call it inertially. A gyroscope up here will precess around as being caught by the whirling of space more slowly than down there.
Yes.
That means that this gyroscope will see that gyroscope going like this, and that gyroscope will see this gyroscope. If you take a towel full of water and you twist it, you think about it, if your right hand sees your left hand going around counterclockwise, then your left hand will see your right hand going around counterclockwise. And so, in that sense, you can distinguish between a towel that's being twisted counterclockwise and a towel that's being twisted clockwise. In the same way, then, as I've described, there is a vortex of twisting space sticks out of the north pole of the black hole. And it's a counterclockwise vortex of twisting space. Sticking out of the south pole, there's a clockwise vortex of twisting space. So a black hole has a very rich structure, all made from warped space and warped time. Then how do you calculate the waves, the stretching and squeezing of space produced by the collision of two black holes? It's very hard because you're not computing how matter behaves in different locations in space as time passes. You're computing how space, distortion of space changes in what? Well, you only have space. You only have time. So it's conceptually, it's very difficult to set this problem up. And then the equations turn out to be extremely, to use a technical term, nonlinear. And that basically means that the entire calculation is forced to be far, far more complicated than you would have expected it to be. And so it did take decades to pull this off. But when it was pulled off, not only did we figure out the shapes of the waves, or analogous to sound, the stretching and squeezing as time passes, but we also learned how these vortices of twisting space behave when the black holes collide, how they interact. We learned when two black holes collide, say with one the spin pointing down, the other spin pointing up, when they collide, you then have four vortices of twisting space sticking out of a black hole, and the hole vibrates, and the vortices fight with each other, and they change their direction of twist. And so this guy was twisting clockwise, and then he's twisting counterclockwise. They're very rich and complex behavior of an object made entirely from warped space and time. And this meant that we, from these simulations, we were discovering how black holes behave when they're quiescent, as in this Kerr metric, but when they're very highly excited. They create a storm, like the storm in the surface of the ocean, how it behaves when there's a typhoon, a hurricane going across the ocean. And so we've learned marvelous things from these simulations, and this storm in the shape of space and time is what is creating the gravitational waves, in fact. So although the waves are fairly simple, they are bringing in us information about aspects of black holes that we didn't even know existed until we started doing these computer simulations. I should back off and say, until my colleagues started doing it. I neither built the LIGO instruments, nor did I program the computer. I just provided scientific vision for both efforts.
We are almost out of time,
Yeah.
so the last question, we have discussed a little bit of theoretical aspects of the whole thing, and now to the experiment. As far as I understand it, you at first refused the idea of this kind of experiment, and for me, even today, it's almost unbelievable miracle that we can measure for 4 kilometers apart large mirrors, the shifting of these mirrors of the magnitude of the thousands of the atom, no, not of the atom, but of the atomic nucleus. I do understand a bit about Roy Glauber's coherent states and squeezed states, but the fact that the interaction of the light, of the laser light, with the matter, which consists of atoms, can be done in such a precision. For me, it's even today, I'm absolutely with you 50 years ago when you refused the idea.
Yes.
I can absolutely understand it. And for me, it's today a miracle. Can you just a bit comment on this part?
So I think the key, first I'll give you a number. So we have to measure the motion of the center of a mirror, what we call the center of the mass, to a precision that is 10 million times smaller than the individual atoms of which the mirror is made. So the center is moving back and forth 10 million times less due to the gravity wave than the size of the atoms. And the mirror's face is all made of atoms, and you do this by bouncing light off the face of the mirror. The key to this is to average things. So we have a laser beam that is about this size, and it goes in, it bounces off of the mirror, and it averages over a very large number of atoms. The atoms are vibrating because they're at finite temperature. It averages over a huge number of vibrations during half of a gravity wave period of oscillation. And the key is to make those vibrations as small as possible and then average over so many of them that you remove that noise.
What you are telling me is that when it cools down, the answer is the Avogadro's number, 10 to the 26, and that's the miracle.
That's the miracle. That's the miracle. Yes, that's basically the miracle. But the issue for me was in the early 1970s. When I heard this idea, I thought, obviously it cannot work. But I had long conversations with Ray Weiss, who conceived the idea, MIT, who in the end co-founded LIGO with me. He and Ronald Drever, who contributed to the ideas. And with Vladimir Braginsky in Moscow, who was, for me, he was among the 2 or 3 greatest experimental physicists of the 20th century. And through these discussions, I, as a theorist, but a theorist who works very close to experiment, I came to be convinced that we might succeed. But it took a lot of conversation, a lot of calculations of my own, thinking about how you deal with the various kinds of noise to become convinced. My colleagues who didn't spend the time to do that remained not convinced. And the project was quite controversial until the day it succeeded.
Okay, unfortunately, we are off the time. I want to, I want to thank you, and I don't know how to do it as deeply as I want to. Thank you.
Let me just make the remark, the people who are the real heroes of this are the 1,000 scientists who made it happen.
Yeah.
And particularly the younger generation. Ray Weiss and I are old men now, but the younger generation who really made it happen in the end, they are the true heroes, and they don't get enough credit.
Okay, thank you very much.
Thank you.
Diskusie pod lampou existujú iba vďaka vašej podpore. Ak považujete program pod lampou za zmysluplný, pomôže nám už 1 euro za diskusiu. Vopred vám veľmi ďakujeme.